So let's consider example 1. We want to find the general solutions of the non-homogeneous differential equations of the form y double prime plus 9y equal to 3 times sine of 3t. I break the problem down to multiple parts so that to hopefully help you follow the procedure in all the calculations involved in finding the general solutions of the differential equations. So part A is to just determine the right-hand side g of t of the non-homogeneous differential equations. So g of t in this case is going to be 3 times sine of 3t. So if you notice, the right-hand side is easy enough for you to use the undetermined coefficients, but for the sake of variation in the parameters, we're going to use that method instead. Okay. Then part B is to find the complementary solutions or the homogeneous solutions to the corresponding homogeneous equations. That is, the homogeneous equation is going to be is y double prime plus 9y equal to 0. Then you turn this into the characteristic equation of the form r squared plus 9 equal to 0, and you could be able to find the root of this equation, and you get r squared equal to negative 9, or r is equal to plus n minus 3i. So this is the complex root with lambda equal to 0 and mu is equal to 3. Therefore, you're going to get the homogeneous solutions as follow. So the homogeneous solutions. You have y1 equal to cosine of 3t, and y2 is equal to sine of 3t. For the variations of parameter, you will need the information of the Wronskian, so we have to do the calculations for the Wronskians of y1 and y2. That is, y1, y2 is equal to the determinant of the form y1, y2, y1 prime, y2 prime. This is equal to the determinant of cosine of 3t. This is sine of 3t. The derivative of y1 is negative 3 times sine of 3t, and the derivative of y2 is 3 times cosine of 3t. That gives you 3 times cosine square of 3t plus 3 times sine square of 3t. Take 3 as the common factor, and you're left with 3 times cosine square plus sine square, and cosine square plus sine square is equal to 1. So this is square. Okay, so you take 3 as the common factor, you're left with cosine square of t plus sine square of t. And this is the trigonometry identity, and that is equal to 1, so the Wronskian is equal to 3, which is different from 0. So when the Wronskian is different from 0, again, the homogeneous solutions are linearly independent, and they form a fundamental set of solutions. Now we're going to use this information to find the form to find the particular solutions of the non-homogeneous differential equations, and the particular solution is of the form. So the particular solution is y sub p equal to negative y1 times the integral of y2 times g of t divided by the Wronskian plus y2 times the integral of y1 times g of t divided by the Wronskian dt. For y1 is equal to cosine of t, y2 is equal to sine of t, the Wronskian is equal to 3, and g of t is equal to 3 times sine of 3t. So you're going to put everything together as follow. So y sub p is equal to negative of cosine of 3t times the integral of y2, which is sine of 3t, times g of t. So g of t is equal to 3 times sine of 3t. And the Wronskian is 3. Plus y2, which is sine of 3t, times the integral of y1, which is cosine of 3t, times g of t, which is 3 times sine of 3t, divided by 3, the integral which is with respect to t. Alright, so one thing I want to mention here that the right-hand side or the forcing term is 3 times psi of 3t, which is mimic the homogeneous solutions. Right? So therefore, when you make a guess, when you use the indeterminate coefficients and you make a trial solutions, you cannot use psi of 3t. You have to do t times psi of 3t to avoid the linear dependency on the homogeneous solutions. So that's one that is another drawback of the indeterminate coefficients. However, for the case of variations of parameter, you don't have to worry about that. You have the homogeneous solutions, and yes, the right hand side mimic the homogeneous solutions, but we don't care about that. We just basically plug into the formula and do the calculations. Alright, so let me simplify a little bit. So 3 cancel out in the integrand, and you still have negative cosine of 3t times the integral of psi square of 3t dt plus psi of 3t times the integral of cosine of 3t times psi of 3t dt. Now the job is to calculate the integral. So the integral of psi square of 3t dt. So as you see, there's no straightforward formula that you can do to find the antiderivative of psi square of 3t. What you do is that you need to turn this into something else. Right? So in fact, you're going to use the double angle formula or double angle identity to rewrite psi square of 3t. So this integral becomes 1 minus cosine of 6t divided by 2 dt. And from here, you break it down into two different integrals. The integral of 1/2 dt minus the integral of 1/2 times cosine of 6t dt. So the integral of 1/2 is 1/2 t. The integral of 1/2 times cosine of 6t, you first pull out the 1/2. And then the antiderivative of cosine of 6t, I'm going to give you 1/6 times psi of 6t. Okay, as you see, I didn't include the plus c in the calculations, even though we are dealing with the indefinite integrals. So this is one of the places that you don't need the plus c for the indefinite integral, in addition to the integrating factor that you see in the first order differential equations. So the reason we don't need the plus c is that when you plug the result back to the formula for the particular solution, you have the plus c on the constant multiplied with cosine of 3t, the constant multiplied with psi of 3t, which is the homogeneous solutions already. So it's just a little bit redundant to have the plus c in calculating this integral. And if you include the constants, the homogeneous solutions will come out again. So that's not necessary. That's just a little bit redundant. So that's why we don't need the plus c in this type of indefinite integral. So that is the first integral. The second integral that we need to take care of is this integral. So we have the integral of cosine of 3t times psi of 3t dt. And again, there's no straightforward formula that you can use to find the antiderivative of this integral, but what you can do is you can use substitution or integration by substitutions by letting u equal to psi of 3t and du therefore equal to 3 times cosine of 3t dt, or 1/3 du equal to cosine of 3t dt. So the integral becomes 1/3 u du. The antiderivative of this gives you 1/3 times 1/2 u squared. Again, for the integral inside the particular solutions of the variations parameters, you don't need the plus c. Okay. Now you need to replace u by the original variable, which is psi of 3t in this case. You have 1/6 times psi square of 3t. So you have everything that you need. Now you're going to put everything back together to rewrite the particular solutions. So the particular solution is you have y sub p equal to negative cosine of 3t. So I'm going to start over here, multiply with psi integral of psi square of 3t, which is equal to this part, plus psi of 3t, multiply with the integral, which is equal to this information. So negative cosine of 3t times 1/2 t minus 1/12 times cosine of 6t plus psi of 3t times 1/6 times psi square of 3t. Now simplify further, you can take 1/2 as the common factor here for the first term, and then combine psi of 3t and psi squared of 3t. So the particular solutions becomes -1/2 times cosine of 3t times t minus 1/6 times cosine of 6t plus 1/6 times psi squared of times sine cube of 3t. And that is the particular solutions of the non-homogeneous differential equation using variations of parameter. Now I'm going to move on to another example, and we're still going to use the variations of parameter to find the particular solutions of the non-homogeneous differential equation. And the problem is set up like this. You have y double prime minus 4y prime plus 4 equal to x plus 1 times e to the 2x. So as you can see, I didn't break it down into multiple parts, but as you see in the last example, the procedure should be that you identify the right-hand side of the non-homogeneous differential equations, you find the homogeneous solutions corresponding to the homogeneous equations, find the Wronskian of the homogeneous solutions, then find the particular solution using variations of parameter. So that is the procedure, that is the process for you to follow with this example too. So here the right-hand side of the equations is x plus 1 times e to the 2x, and this is g of x. So the variable is slightly different. Instead of g of t, now we have g of x, but the meaning is the same. So the next step is to find the homogeneous solutions based on the homogeneous equation. So from this differential equations, the homogeneous equation is of the form y double prime minus 4y prime plus 4 equal to 0. Then you turn these equations to the characteristic equations of the form r squared minus 4r plus 4 equal to 0. And then you rewrite the quadratic equation as r minus 2 altogether square equal to 0, and you solve for the root, that is r equal to 2. Now you have the repeated root. Then the homogeneous solution is of the form y1 equal to e to the 2x, and y2 is equal to x times e to the 2x. And if you wonder again where these two solutions coming from, I could recommend you to go back to lecture 10, where we talk about method of characteristic for the repeated root and reduction of order. When you look at the right-hand side of the non-homogeneous differential equations, you have a product of linear functions and exponential functions, which is okay for you to use the undetermined coefficients method. However, the right-hand side mimic the homogeneous solutions. That is, you have e to the 2x for the first solutions and x times e to the 2x for the second solutions. Therefore, using the method of undetermined coefficients, when you make the trial solutions, you have to go up to x squared times e to the 2x, which is going to make the problem more complicated. However, we can avoid all of that. We don't care about if the right-hand side mimic the homogeneous solution or not by using the variations parameter. Then, now the next step is to calculate the Wronskian of the two solutions, y1 and y2. So the Wronskian is w of y1, y2 equal to the determinant of y1, y2, y1 prime, y2 prime. This is equal to, y1 is equal to e to the 2x, y2 is x times e to the 2x. y1 prime is 2 times e to the 2x, and y2 prime is 1 times e to the 2x plus x times 2 times e to the 2x. You calculate this 2 by 2 determinant, you get e to the 2x times e to the 2x plus 2 times x e to the 2x minus 2 e to the 2x times x e to the 2x. Then you distribute e to the 2x into the parentheses. You get e to the 4x plus 2 times x times e to the 4x minus 2 times x times e to the 4x. And these two terms cancel out, and you're left with just e to the 4x, which is different from 0. So this indicates that the two solutions, y1 and y2, are linearly independent, and they form a fundamental set of solutions. Now with the Wronskian, with y1 and y2, and with the right-hand side, you can now write out the particular solution using the variations of parameter method. So particular solutions. You have y sub p equal to negative y1 times the integral of y2 times g of x over the Wronskian dx plus y2 times the integral of y1 times g of x divided by the Wronskian dx. So the formula should be the same as before, as the previous example. Again, the variable is slightly different. Instead of t, we have x, but they have the same meaning. So y1 is equal to e to the 2x, y2 is equal to x times e to the 2x. The right hand side is x plus 1 times e to the 2x, and the Wronskian is equal to e to the 4x. So we're going to plug everything into the formula. So y1 is e to the 2x times the integral of y2, which is x times e to the 2x, and g of x is x plus 1 times e to the 2x. Altogether divided by e to the 4x dx plus y2, which is x times e to the 2x times the integral of e to the 2x times x plus 1 times e to the 2x, altogether divided by e to the 4x dx. Now we're going to simplify e to the 2x with e to the 4x here. Similarly over here, e to the 2x, and e to the 4x cancel out, and you're left with negative e to the 2x times the integral of x times x plus 1 dx plus x times e to the 2x times the integral of x plus 1 dx. So again, we still have two integrals to evaluate. The first integral is the integral of x times x plus 1 dx. You distribute x, you get x squared plus x dx, and you find the antiderivative of this, you get 1/3 x cubed plus 1/2 x squared. And again, the indefinite integral in this case doesn't need the plus c. The reason for that again is that when you have a plus c constant and you put it back in this multiplications, in this product, you will get the homogeneous solutions back. So adding the constant here is a little bit redundant, it's not necessary. Now for the second integral, you get the integral of x plus 1 dx. So this gives me 1/2 x squared plus x, so there's no plus c in this case either. So the particular solutions is, you have y sub p equal to negative e to the 2x times 1/3 x cubed plus 1/2 x squared plus x times e to the 2x times 1/2 x squared plus x. Then you're going to distribute and combine like terms. So negative 1/3 x cubed times e to the 2x minus 1/2 x squared times e to the 2x plus 1/2 x cubed times e to the 2x plus x squared times e to the 2x. So the particular solutions is going to be 1/6 times x cubed times e to the 2x plus 1/2 x squared times e to the 2x. Then after you get the particular solutions, you can combine this with the homogeneous solutions to write out the general solutions. So the general solutions is y equal to y sub h for the homogeneous solutions plus y sub p for the particular solutions. Now for the homogeneous solutions, that's going to be c1 times y1 plus c2 times y2 plus y sub p. For y1 is equal to e to the 2x and y2 is equal to x times e to the 2x. So you get c1 times e to the 2x plus c2 times x times e to the 2x plus the particular solution, which is 1/6 times x cubed times e to the 2x plus 1/2 x squared times e to the 2x. And that's it for the problem, and that's it for the lecture note involving the variations of parameter. So the idea of variations of parameter is that this is not a solutions method to solve for the solutions of non-homogeneous differential equations. And the focus is that sometimes the right-hand side of the non-homogeneous differential equation is complicated enough that you cannot use the method of indeterminate coefficients. And also, based on the two examples that we have in this lecture, you see that sometimes it's a lot easier to just use variation of parameter and don't have to worry about the linear dependency of the right-hand side versus the homogeneous solutions. Okay, so that's it for me. Please let me know if you have any questions. Thank you.